Welcome everyone to the DCSC Lunch Colloquium. Today's speaker is Anil. He has been actually with us for quite some time. Before that, he did the master in mechanical engineering in Belkent University in Turkey. And after that, he did a PhD in mechanical engineering at the University of Michigan. And then since 2024, he's at DCSC, right? Yeah. And today he will give a presentation on safety critical control with control barrier functions, backup construction, and robustness. The floor is yours.
Thank you, Bob. Thanks. It's such a privilege to be here. And I have to say thank you also for you guys to be here, choosing to spend this very beautiful time rather than being outside, being here, listening to what I have to say. I'll try to make up for it, but I cannot guarantee. So if you have any objections at any point, please let me know. And I'm also sorry for this, but I choose to use a stick as well. Hopefully it's going to be useful. Today, I will talk about safety critical control, what it is, and how we can do that using the control barrier functions. I know it's a very popular topic, especially in the last 10 years or so. Hopefully, I will be able to draw a nice picture for you guys. And I will particularly focus on two things: backup construction, basically how can we construct safety control barrier function, and then how can we do to improve its robustness or resilience against some of the things that we may not choose to consider while design. So the motivation, I tried to cut it short because I think we also are a little short on time anyway. The motivation is basically, okay, we need safety critical control because all of these technological developments lead us to all these marvelous engineering systems where they now operate within the presence of other human beings and other agents as well. Now we have to make sure that some of the properties of the system should be limited. This can be the distance between cars, right? So I do have an example, actually, we'll go through that. But the good thing, or the thing that is required for safety critical system, people try to kind of differentiate themselves from the classical control is we do need some formal guarantee, so we shouldn't really do it in a heuristic way, or maybe like trial and error, etc. So what do we need is we need to design a controller, and before actually implementing it, we should have some certain guarantees. This is the content of my talk. I'll talk a little bit about the foundations of the control barrier functions. Why do we actually use it? Why it's very nice and easy? And then how can we actually certify some certain functions as control barrier functions? And it's going to be basically backup constructions. And then how can we robustify them? This is a model-based approach. So the model and the real plant doesn't really match. How can we actually improve the resilience, right? I'm going to briefly talk about input to state safety in that sense. And throughout the talk, I will use a safe car following it as an example. So we talk about safety and we talk about guaranteeing safety. Now we need to make a definition what it is. So this kind of definition will go all the way to the end of the talk. What I mean is we have a system that is running the continuous time, and we have a set of initial conditions, and we have some sets that I don't want to be in. And basically, I'm going to use the phi throughout the talk to define the solution of this set given the initial condition. What we mean basically safety is anywhere I start in this initial sets. If throughout all the trajectories I do not hit anywhere in the unsafe set, then I am safe. But this safety definition, as much as it is relaxed, it doesn't really give me a lot of constructive ways to design the controller for that. This is why we actually prefer this function-based definition. It's slightly more restrictive than this, but basically we are trying to find a quantifying way to basically, or a way to quantify the safety number. So if I can find a set that is the zero superlevel set of this function, if this set is a subset of the initial condition, and if I know that for every initial condition, if I roll out these trajectories, the function is always positive, then I am safe. So this will be the safety definition that I will rely on. How do we make sure the safety actually satisfies before implementing into a system and making a lot of experiments and heuristic ways or the trial and error ways is through this set theoretic safety verification. This basically, I think, sentence summarizes it very well. So basically, we are trying to calculate find safety as a property of a system without really having to calculate all these trajectories for every possible initial conditions, right? And the developments for this line of work goes all the way back to the Nagumo's theorem around the Second World War, where all this science and progress typically peaks throughout the world, unfortunately. But Nagumo basically found a way to, we say, very tight way to identify safety for a nonlinear system. It relies on this idea of tangent cones, or somehow I think some people call it tangent cones. The tangent cones are basically at a point, the set of directions where if I go infinitesimally in that direction, I will still be in that same set. So this is basically what it says. It's a fancy definition, but I'm not going to use this definition at all. Nagumo basically binds this definition to the safety. And what I mean by tightness is actually he uses if and only if to bind this. So it is goes both ways, it's pretty important. If my model at every point in this set falls into the tangent cone, then I do have safety. This function that I use to define the set, if it's Lipschitz or smooth, then basically this tangent cone can be seen as a subset of this condition that I can use to calculate this another set. This is basically the generalized gradient of this set. And if for the smooth case, I can use the gradients to calculate the half space, basically. But this is actually like a kind of a necessary condition, but it's not a sufficient condition to give me the tangent cone. If I have some non-degenerative boundary condition on the basically everywhere on the boundary, that means that if my function is smooth and if its gradient doesn't really disappear anywhere, or in the generalized case, if 0 is not a part of the set, then this becomes equivalent. So this kind of half space now becomes my tangent cone. And I can use this to basically define safety critical controllers. This is basically kind of what is lying underneath. From here, we kind of jump to the control barrier functions because tangent cone condition only gives us something to work on only on the boundary, but we do not really like this because we are trying to design a controller. And if a condition will tell you nothing until you hit a boundary, that's not really very practical. So what you want, suppose is a condition that can also be extended towards the set as well. So maybe gradually you can actually approach to the boundary and stop somewhere on the boundary. And this is where control barrier functions come into the picture. It is kind of inspired from the Lyapunov functions where we are trying to find this positive definite function, right? And by basically upper limiting the time progress of the positive definite function, we are making sure that trajectories converge all the way to exponentially to the origin. Similarly, in the barrier function, you can think that function kind of flipped and kind of pulled it a little bit above so that you create the set. Now, instead of upper bounding, you can lower bound the time derivative of this function along all the trajectory so that what it tells you that you can approach to the set boundary, but exactly on the same boundary, this becomes 0, so you cannot leave. So this is a very basic condition that I can use to also design the controller. This is basically the theoretical progress of this method. So we do find a way to define what a function is, whether control barrier function or not. it relies on finding a class kappa function that can be that can lower bound the time derivative of this function along the trajectory. A class kappa function is just basically a generalized version of a linear function. It's continuous, its argument is zero, it is zero as well, and it is monotonically increasing. And the theorem tells me that if there is a control barrier function for this state, for this system, then any local Lipschitz continuous controller that satisfies this condition is going to keep me safe. So this basically deals with the safety part of this problem, but I think in modern engineering system, we actually kind of want to deal with all the other things as well, such as stability and optimality. Recently, there are some works that are threading the difference between these three edges of this triangle, such as the constructions of Barrier-Lyapunov functions. And recently, Miroslav Krstić had a paper about the inverse optimality, kind of trying to find a way to get the safety, but also can we be more optimal. But in this talk, I will talk about one particular type of controller that I can design using control barrier function. It's going to be called safety filter because it's modular, it's very simple, it's very popular for its flexibility. Basically, it takes whatever the controller. It can be another optimal controller, but you do not consider the constraints. It can be RL, can even be human operator. I will show you some results based on that. Basically, what you need to do, make sure is the outcome of this controller needs to satisfy this control barrier function condition. As I said, I will use the car as the example because it's very intuitive, it's very simple. You can see I'm going to design a controller to control the gas and brake pedal for this car based on the information that I'm receiving on the other vehicle. The distance, the speeds are here. Basically, I just don't want to hit the other car. I still want to add some certain margin to my safety measure. There are some practical reasons, not really that important. But basically, the idea is I want to be always in the green side of this D state space. And this is obviously always going to be positive for the headway distance anyway. The trick here is, based on this construction, I do have a certain function, but for now, I'm not checking whether it's a control barrier function or not. Let's see what happens. The nominal controller, I'm going to take as a human driver. So again, I'm not dealing with the optimality and the stability of the things, but I'm kind of focusing on the safety. Let's see. For initial results, I used a high-fidelity simulator called CarMaker. It's pretty nice. You can get all the parameters for your car so that you can get a precise model. And you kind of need to hack the car a little bit by using or trying to get the gear maps and the brake maps and etc. But in the end, it is doable. And this is what I did. So first, I'm going to give you the results for the human driver. There's no safety filter here at all. This guy is just like not really minding his business, not really pay too much attention to the road. This is a car maker model. I don't know really what is underneath running. As you can see, there are some instances where the safety is violated. It is the safety the way that I define. It's important because it actually never hits the other car. The headway never becomes less than zero. But it's not important. We are after some guarantees, some formal guarantees that this function will never be negative. If we put the safety filter on top of it, then we actually get it. It's pretty neat. And this is another very important plot that I want to show you. This is basically whatever my controller calculates. This is important because so far I haven't talked about this maximum brake. As you can see, it is kind of going within the maximum until maximum brake anyway. So it's not a problem for now. I got the safety, I got the maximum break here, and this controller runs within the input boundaries anyway. But then what if we actually kind of try to push this controller a little bit more? And the easiest way for me was to add this trailer. And because if your controller demands a similar deceleration, now you need larger braking torque to realize that because of the increased mass. The idea is pretty simple. If you do that, you're going to see mostly you are still fine. But towards the end, basically, this was a certain speed profile where the leader is making a huge brake towards the end. You see that you're no longer safe just because the controller demands more than what your car gives. It is because this function doesn't have a certification. And this is pretty much the Achilles heel of the whole idea of control barrier functions. The main criticism is how can we make sure that, well, if you know a function that is control barrier function, it's pretty easy. You just construct this control. But how can you actually make sure that a function is a control barrier function? This goes back to the discussion of control invariance, as I'm sure some of you at least know. This type of discussion for the MPC, what I'm talking is about recursive feasibility, basically, right? Control invariance set research goes way back, I would say 30, 40, 50 years. The idea here is now you have a control. I want some guarantee about the feasibility, whether this set can actually be made safe within what is given to me. So if I can get this guarantee of control invariance, then I may find a way to construct a control barrier function. So we are kind of taking one step backward from getting some guarantees of the control invariance set or constructing this control invariance set. As I said, it's very popular, very common problem. People are trying to solve this problem using methods that are mostly numerical, I would say, like backward set pruning. Basically, you start with a set and check its boundaries. And if a point in the boundary doesn't really give you safety, then you kind of get off that point and get another set. It's a very iterative way. You can construct the problem as a Hamilton-Jacobi-Bellman equation, and you can try to solve that. I would say that is actually the most methodic way of solving this problem. Or if your set and your dynamics are nice in the way that they're semi-algebraic, they're like polynomials basically, then you can use SOS or some other semi-definite programming optimization to construct these control invariant sets. But within the control barrier function community, this backup trajectory approach is becoming more and more popular. This is what this approach relies on a backup controller. It can be coming from some heuristic design, any way that you think is going to work for you. Basically, it's going to keep you as safe as possible. So if you plug in this backup controller back to your system, you will have these trajectories basically rolled out. And based on these trajectories, you can actually construct a set that is guaranteed to be control invariant by construction. So basically, at any point, if you roll out these trajectories, if trajectories doesn't really leave this set for all the time, well, then basically not only that point, also all the point in the trajectory actually is part of a control invariant set. This is an implicit way. You cannot really calculate an explicit formulation for this set, but it is okay. I can still work with that. One practical thing here is obviously this time goes to infinity thing becomes problematic when I try to implement anything related to that. So basically, people use a backup terminal set, kind of try to use a finite time and whether see that they actually end up in that backup set or not. This is a cool diagram that tells the idea. The big airplane is the real trajectory, so this is what actually controller does. But the real one, the small ones are basically the simulation rollouts. So at every point, you make sure that the safest controller is gonna bring you back into this backup set. If that's the case, then you can use that function to design a safety controller that is going to keep you all this throughout the trajectory. At the end, you will still, when you roll out this trajectories, you're gonna be in the backup set. So this is the idea. It's not really groundbreaking or anything. I'm sure similar ideas are discussed within the MPC and other optimization control frameworks. The problem here is control invariant sets do not actually necessarily admit a control barrier function. So this side of this relationship is established using Nagumo, but that side is actually a little bit tricky. By using the converse safety theorems, we can actually find a condition about the set such that the other way is also true too. That means that if we do have a controlled invariant set, and that set is compact, then that set necessarily admits a control barrier function. This is a really powerful approach. Another problem with the backup set is the continuity of the time. We need to discretize it, and in the implementation, this is what we did basically. The whole idea at the end of the day is we can come up with this kind of, I merge these two things together and come up with a way to show that using the backup trajectories, you can ensure a way to design a control barrier function. So now we have a way to guarantee the feasibility of the safety filter as well. And if we implement this to the system, we got the premise. So we do have the safety, and the controller doesn't need to violate to get the safety. But the problem is now you are kind of rolling out some certain trajectories in the simulation, and you have other agents in your system. You have to have an idea about what the other people or other agents are going to do in the, at least within some certain window. If you always expect the worst from them, you will get a very, very conservative result. If you exactly know what they're going to do, then you get a really good result, but, well, how can you know that? And this brings into the question whether can we actually have a nice estimate what this car in front of me is going to do within like 5-6 seconds. There are traffic models that gives me such estimates, and I believe the simplest and the most intuitive one is this one. It relies on the connectivity, which is becoming another hot topic actually. So what is going on here is if we have some certain way to get the GPS data of the first car, then we can maybe shift it a little bit in time to estimate what the blue car is going to do. So if we get a brake for the first car, then this brake actually progresses all the way to the blue in time. And this estimation is actually given here. It's pretty decent one. And this is through the simulator, by the way. This is not MATLAB. So all these cars run some certain driver models to themselves. I don't really know what they are. I am just designating what this car is going to do. And basically by putting a couple of seconds backward, I have an estimate of what this car is going to do. So if I implement that, I do get a pretty decent result too. All right, so this is pretty much the first half. In the second half, I'll a little bit talk about the robustness, but I want to stop a little bit if you have any other question. I realize maybe I'm going a little bit too fast. Yes.
So you had the definition of the Smith, you had the actions. There is a distance between set and the vector X. So I was wondering what's the definition of that distance?
I'm sorry, I'm not sure if I understood that.
So in one of the first slides, it's the concept of tangent.
The tangent column.
Yeah, just like that. You make it.
Yeah, so basically you're at a point, and these are the directions that from that point, if you go from that direction, what is your distance to the set?
This I think the sense of linear.
Yeah, I'm sure there are like ways to specify what this distance means, but it's not very important. Yeah, I'm not sure if it's gonna be very. So the thing is, this tangent column is actually, if you're in the interior of the set, it is everywhere. If you're outside, no point. So it basically is very important on the boundary. And to characterize the boundary, we have basically these things. So this type of definition, I put it here, but it's not really like definition itself is not being used anywhere in the controller. It's rather this or this generalized gradients.
The impact on the Nagumo results change the distance between some other type of. For example, if let's say you're using a treat and the unit policy sequence, now the specific types of behavior, but let's say you're using like no one is used in that some other specific something or something insurance.
So are you saying like in some there are some certain definitions, distance definitions where this may hold, but in some other definitions this may not hold? Interesting. Yeah, I'll think about it. You had a question too.
Yeah, for the case where you use the estimator at the end,
Mm-hmm.
do you still have all of the guarantees? Because I understand with the Oracle you have a guarantee because it's perfect.
Yes.
Worst case is obviously guaranteed because it's worst case.
No, it's a good question because this is where I'm gonna come actually. The answer to your question is no, because I'm not robustifying my methods based on whatever the error this estimator may give. But there may be ways to do it. And exactly this is where I'll come to. I will discuss the robustness, not relying or based on the estimate error. It will be based on whatever. I think it can be more generalized, but I think maybe you'll get a better idea what it is. So no, actually. So it's just there are some certain resilience inherent to the model, to the method itself that even with some estimation errors, I do still have what I want.
You have an equivalence condition for the barrier function, the X compact. What kind of H satisfies like this? That for example, linear doesn't satisfy, or what kind of?
No, linear function necessarily defines a half space. No, it has to be, no, linear functions do not work. So yeah, it has to be like maybe a polynomial that you can. So the thing is, I'm kind of skipping a lot of stuff here, but there are extensions of this work that also work for half space type of formulations as well. This is just if it's compact, you get the result directly. You don't have to make any changes. But if it's not the case, you can make some changes and you can still get this result. Yeah. Basically, if you have a half space, then you may not be able to find the class K function. That's pretty much the problem. Sorry, Patrick.
All this theory is in continuous time, but in practice, when we implement these polars, we do it in discrete time.
Mm-hmm.
Is there somewhere bridging that gap? Also, because we can't solve the quadratic program continuously.
Mm-hmm. The funny thing is, that's a good question, but about solving the problem, this quadratic programming, particularly for this example, I didn't show it to you, but this we have actually closed form solution for this problem. It is just basically a min switch controller. This whole thing becomes. But for a general setting, you're right. So it's a QP you need to, or maybe it's a QP or maybe not. You still need to be able to solve that. For implementation and the computational talk, there are some people who are trying to find approximations, but I don't really pay like too much attention towards that direction. But whatever you work in the continuous time state, as long as your model is accurate enough to capture what is going on in this system in a continuous time domain, then the theoretical guarantees should still hold. I would say probably for robotics, this approach is a little bit more. There are methods like the Lagrangians and the Newtons and etc. Right? They are going to give you continuous time models. So I feel like people use this for those type of things. But anyway, so let's go to the robustness. One of the things that you can see, or at least my personal experience kind of gave me, is as you go up in scale in the cars, the problem gets more and more complicated. So far we were talking about the passenger vehicles, for example. It was somehow easier to model, and you actually have a really accurate model that is representing the system. You can check it using the experiments. When we now started, when we implement the same controller to the truck, we will start having some problems. But even then, you still need to push the controller to the limitations, because otherwise you still have a nice controller that is running even on the highway. You still have nice reaction that is you're gonna see a cut-in, and the controller is not like going crazy or anything. It's not gonna give you unreasonable reactions, basically. So you can see the headway, there's a jump, the radar detected it, and my controller is gonna slightly give me brakes. So it runs pretty good. But then obviously we are doing PhDs in the academicians, we need to push the controller all the way, right? What can this controller do if there's actually like an emergency brake in front? So these cars are talking to each other through these devices. Based on that, I do decide whether to brake or not. So the thing is, in the emergency brake situation, I don't get the physical collision, but the formal guarantee does not hold. And that is not surprising because of this theoretical model that assumes there's an ideal powertrain and brake, which is somehow a reliable assumption for passenger vehicles, but it is not the case for trucks. Because in order to get a very high braking torque that is required to stop the truck, you need to use air brake. Now that you have some certain, almost to the 1 second of reaction when you make the command, it's gonna come a little bit later. And this system is very hard to model. It's very complicated. There's some safety checks and etc. So rather than increasing the fidelity of the model, what if we just treat that as a disturbance and design our controller according to that? So there are robust methods in control barrier functions. It's an ever-growing literature, I would say. Every year you'll see maybe 10, 15 papers. The idea here is instead of just making sure the controller is going to keep the system safe based on just a single vector, now we have a range of vectors, right? If the nature of the uncertainty is distributed, then the control barrier function constraint can be changed towards a chance constraint. Then it's going to give you a probabilistic safety result. So you're going to be safe to 1 minus epsilon chance. If you have a deterministic bounds, basically, if you can have a very clear idea about how disturbance is going to affect your system in the worst case scenario, then you can approach this problem in two different ways. One is the robust control barrier function. Basically, you want to kill the effect of disturbance with your controller. And that's one way. It's very popular. It's very intuitive. The other way that I spend a little bit more time, I would say, is, okay, there's a disturbance. If you can actually kill the disturbance using your controller, then do it. But what if your disturbance is also a function of your input as well? Like, what if you're actually playing a game that you're actually also changing what the disturbance is going to act in the future? In that case, the best thing we can hope is a graceful relaxation of formal guarantees. What we mean by that is, now instead of getting a 0 on the right-hand side, can we find a lower bound that is going to give me, as I said, a safety relaxation? And that relaxation is going to scale with how much disturbance is going to be. But this is very much like a kind of a classical control approach, where I'm trying to characterize how much this disturbance is going to affect the outcome of my plans. And I can do that. There are some sufficient conditions I can construct based on the control barrier function. It's not really important what it is, but basically you can calculate such function. So this new addition term is going to give you some extra robustness to your system. And this epsilon appears here and here as well. That means that you can actually tune it. So if you want practically 0 degradation for safety, you can do so by increasing this epsilon very, very much. But in that case, you get a very, very conservative result. So there's a trade-off here to strike. In the end, this controller can be implemented. It is very simple. It's just like another line of code, but for this system, I think. And this is the safety degradation guarantee that I calculated. And this does work. So input to state safety is very promising, I would say. There are some works that are kind of extending this towards the multi-agent systems. I think in the near future, maybe you'll hear more about this idea. But by no means, input to state safety is a way to robustify the system. This is from one of my papers, maybe 3 or 4 years ago. And ever since, I would say, the amount of work tripled, maybe even more. And people use every ways to kind of eliminate the unnecessary conservativeness of coming from the robustness as well, like adaptive control, disturbance observers. Some of these methods use data to learn the nature of the disturbances and etc. But what I mean is, people work there. It's a very hot topic right now. In the end, what we want to reach is an algorithm that runs reliably in the long term and safe in the presence of other agents. And if we can achieve that, I believe this is an improvement. And this actually ends my talk. Yes.
So I was trying to understand. So if I talk about the disturbance in terms of the probability that we have given, so the air brake, the delay in the air brake is the disturbance, right? Or not?
Yes.
And I'm trying to understand, if you have a delay in the air brake, then how do you compensate with some other inputs in terms of the practical example? Because you say that air brake is the last condition, like if you have some emergency condition.
Mm-hmm.
So what extra sort of input or breaks you
So
want to add?
when you are calculating the control inputs, you are implicitly considering that in the calculations. So that actually is going to be here. You pay a price, right? And the price you're paying is actually shown here. So this term, extra term, is going to give me some sort of robustness. And this is the price that I'm paying, because if I don't add that, I don't have to follow the car from that much distance. But as soon as I put that, it's kind of a proactive way of, wait, if I do the brake, it is going to kick in 1 second later. So what if I put something that possibly maybe follow the other car?
Understood. So essentially, it means it boils down to the fact that your estimation of disturbance has to be bit like from some time before, right? So suppose there is some emergency, like a stop, then you have to estimate that fact that the car is stopping at this emergency situation a bit before, so that you can incorporate that a priori with this new.
Not really. So this thing works as long as your disturbance is bounded. As long as you have a bounded disturbance, you will get a characterization of safety degradation. It doesn't matter whether the car in front of you is going to brake or not. As long as you assume that the car in front of you is going to behave in a certain window, then you do get this. But the problem is that window can change based on the way that you act.
Oh.
This is the shortcoming of these approaches, because this assumes that you can actually always calculate the worst case scenario and you can compensate that. But ISSf basically tells you that, well, maybe if you play the game, the other person changes, so the bounds change now. So this is more desirable to get a relationship between how much that disturbance acts on your system and
Thanks.
how much the outcome is going to change. Yeah, thanks.
Thanks for the talk. I have more a speculative question. So with some postdoc in my group, we use barrier functions to build a fault detector.
Mhm.
It gives you some guarantees on how much time you have before you exit the safe set.
Mhm.
When you were talking about your backup controller, I was wondering if that maybe can be used to build a fault tolerant controller that you switch to and you have an anomaly. I don't know if this makes any sense.
I think it does make sense. But for fault tolerant stuff, I was more thinking about the input to state safety, because you do have a degradation of your safety, a way to characterize it. So if a fault happens on your system, you fall back to that guarantee. But this, I haven't thought about it exactly, but I believe it can be done, because this is a very flexible way of constructing something. You basically, it's very intuitive, right? You pull out something and you're gonna, based on what's gonna happen in the future, you may change your behavior. I think it makes sense, but I need to check in the details.
Oh.
Yeah, well, I think we discussed about that before, but I'm willing to maybe like read a paper, and that would be nice. Thanks for the question.
So let's thank Anil again.